If you are reverse engineering as part of the CTF, understanding what binary does is one thing. The other thing is getting the flag. In many cases, the flag calculation is an expression that we need to reverse to get the initial flag values. If we don't know how to get the starting bytes of the flag, this is where SAT solver comes in. Z3, also known as Z3 theorem prover, is a satisfiability modulo theories solver developed by Microsoft. Z3 allows to write expression that will be evaluated to give back the values we seek. In this video, we will see how we can use it to solve CTF challenges. Let's start with this simple example. If you want to find all the solutions to the following expression, x squared minus 2x minus 3 equals 0, we can write the following Python script using Z3 and run it to find the correct values. Starting from the top, we import everything from Z3 and we create a variable s to be our solver. Next, we defined one variable called x that will be of type real number. Then, we add our expression to be solved. It is written as it would be a normal Python expression. Next line is important. We ask our solver if it can give us a solution comparing the result of the call check with SAT. If it is true, we can print the solution getting it from the model. If not, Z3 cannot help us. Running the script will give us the solution. Even though it is a quadratic equation that has two solutions, we only get one. If we would like to get both of them, we would have to restrict Z3 to exclude the one solution we've just got. Let's see the updated script. Now, running the script, we get both of the solutions. This is important to remember when we try to find the flag, as sometimes if we restrict our solution too little, we might get the wrong result. Z3 supports other variable types such as int, bool and bitvec. The last one is probably the most used in CTF challenges, as it supports the operations that are present in such challenges, for example XOR. Okay, but how solving rather simple math expressions can help us with CTFs? Let's see a bit more complex example from Flareon 2024 aray challenge. It was a Yara file with rules that would indicate when a file with correct flag is found. If you don't know what Yara rules are, feel free to check that over the internet, but it's not required to understand the later part. We do have a description of this Yara file and a bunch of expression that has to be checked to determine if the file is matching or not. The conditions are based on different things. It could be some specific file properties like file size or certain bytes equals to specific value. In this example, there are even external hash functions used to determine that the hash of specific characters is equal to specific value. We can see that three different algorithms are used: MD5, SHA-256 and CRC32. And our task is to solve this using Z3. We could code all those rules that are in the Yara file manually, but that would take ages. Probably better would be to parse it and generate Z3 rules based on the conditions that we encounter. Let's start small. As we don't need the metadata for the parsing, let's strip that info and only keep the rules. We start by loading the Yara file content and we split it by the keyword end. That gives us the array of all the rules that we need to process. Next, we will need some imports. This is an obvious choice for challenges of such type. Now, we start with the main part of the solution. We need a solver and variables for the currently unknown characters. From quick look at the Yara file, we know that it will be 85 characters long, so we can declare that many bitvec variables. The first rule is the one about the file size. We can just skip it. We've already constrained ourselves to such limit by creating that many flag bytes in the line above. Let's start processing rest of the rules. In few places in the conditions, file size is used to represent the value, but we already know that it has to be 85. So if anywhere in the rule we encounter that name, we'll replace it with the number 85. Rules are following a pattern, so we can handle them together. We can distinguish three different groups of operations: uint8, uint32, and hash. It might be possible to parse all of them with some nice Uber expression, but for better readability, I will do them as a separate chunks. First, uint8. First, we will match on arithmetic operations: AND, division reminder, XOR, add, and sub. Next, comparisons. Lastly, to match some XOR operation with 85, our file size. And if we cannot match to the above regular expressions, we will just print it. Now let's add the lambdas. Math operations are taking three arguments and creating Z3 rule between them, just with a different operator. Comparisons are taking two arguments to create Z3 comparison expression. Now uint32. There is less variability there, so we can handle them with just one rule. And of course, we need our lambdas that does the jobs of creating Z3 expressions. One extra thing we need is a function that will convert 4 bytes of the flag, written as a little endian, into a 32-bit value. This is exactly what toUint32 function does. Now, let's deal with the hashes. They will be processed in two phases. First, we'll extract the hash name and the character number from which the hash calculation begins, and the number of characters that will be used for the hash. We will store those info for later. Let's add lambdas for the hashes. And arrays that will store the hash info. When we process everything, we need to continue with the hashes. Good for us that all the hashes uses only 2-letter long input, so we can actually pre-calculate all the possible values and check which one gives us the hash. When we find those values, we instruct Z3 to constrain characters that build hash input to be equal to the found characters. We do the same for SHA-256 and CRC32. And that's it. Now we can call the check method and see if Z3 is able to calculate the input characters that will fulfill all the rules that we just wrote. And if so, we can print the result. Running the script will give us the flag. While Z3's basic solving capabilities are powerful, in the next part we'll see situation where we need more advanced techniques like optimization to handle more complex challenges.